All right, so I think you're good on this stuff. Let's just make sure you've got some of the specifics down. The shape of a graph, the way that we usually present it in calculus, is basically you can use calculus to completely graph a function, right? So using the first derivative, what can I obtain with the first derivative? Max or min? That's not what I want to write. Okay, what else? Mathematically, calculus-y, what would I call that? The slope is positive, the function is increasing or decreasing, right? What can I grab with the second derivative? Yeah, point of inflection or concavity. Okay. What can I get from the original? Let's go there too. Pre-calculus. Oh, come on, folks. The easy one. Zeros. All right, so if you know the zeros, you know the mins, maxes, the increasing and decreasing concavity, all that stuff, you can graph this really easily, right?
And if you know the relationship between all those things, I mean, by now, we should probably all know that.
Okay, so for some of the more difficult functions, like, you know, cubics, quartics, etc., some of those ugly polynomials, this helps a ton.
Yeah.
Quadratics, obviously, probably not, but possibly. Okay. So, how do we determine? So we've already done all these, right? How do we determine points of inflection and concavity? That's our focus today. Finish that off. Okay.
Were we going to learn what the prime of 3 is supposed to do?
What? F prime at 3?
The third. F triple prime?
Triple.
Yes, that. Whatever. Weren't we going to learn like what that calculates?
And that's just the third derivative. That's what it is.
I know, but like it doesn't. In relation
it's not,
to the graph, like what does it tell you?
well, you could calculate the rate of change of acceleration. Right? Does that mean you're looking at position, velocity, acceleration? Position, the rate of change of that is the derivative. The rate of change of the derivative is second rate of change of.
Yeah, that's true.
Right? I'm sure there's somewhere to use it.
The rate of change of the rate
Be
of
honest.
change of the rate of change of acceleration.
Yeah. Well, it might, like, let's say you're flying to Mars. You're going to require some pretty precise calculations there, right? It might matter.
Yeah.
I don't know. That's a speculation on my part. But
We should just make it so the ship is, you're able to steer the ship so that you know how to calculate.
That's great. Because you
That'd be
can
a long
totally
time
steer the
steering.
ship as you start.
yeah.
The base work, huh? You set a relatively correct course and you just adjusted everything.
Or let the computer.
Every major mistake is everything caused.
Or just make
it easy
Yeah,
on
and
the
then, like,
long run. You just
Going in and jump, like, oh, this is like this and this is wrong.
Okay. Moving on to the actual mathematics and what you're talking about, so you can get to that point, right?
Sure.
So you can be on a spaceship for 6 months flying to Mars. All right. Points of inflection of cosine x on 0 to pi. All right. So we have to go second derivative equals 0, solve, right? What's the derivative of cosine? Is it negative sign? Or cosine? Yeah, you're right. And the second? Okay. is that 0? Same where cosine x is 0, right? Which is at? Good circle.
That's just gonna haunt us. 0.
It's going to haunt you the rest of your life. That would be sine x.
Pi over 2.
Again, just, circle reminder. Where is the x value 0? Right? That is pi over 2 and 3 pi over 2. Okay. All right, are we done? No, you're not.
No.
Points of inflection, you need what?
Sign change.
Sign change. The concavity actually has to change, right? So what are we going to test, the original, first, or second? Yeah. We're testing for concavity change. We need to test the second derivative. Again, always pick easy values. So negative cosine at 0, negative, right? Negative 1. Negative cosine at pi is positive 1. And at 2 pi, we're back at negative, right? So those are points of inflection because there's a sign change in the second. A concavity change, right? Good? On what intervals are we concave up? Yep. Okay, so you can write interval notation, right? What about concave down? Nope, sorry. I'm not listening to you right now, but I'm writing what you're saying. What's the interval? 0 to pi over 2. 2 pi. Yeah, don't forget the... On polynomials, it's usually the infinite is in behavior, but they limit
If it was
us.
infinite, since it's a sine wave, would you not be able to say that? I mean, cosine.
If this wasn't here, is
Yeah.
that what you're saying? Where is it concave up?
You
We would
could
just
say
have to-
negative infinity to.
No,
No, we would have to increase
because it
by,
still oscillates. We're still going to have this coming up.
That would be.
we would have to increase by pi.
Yeah, we're not going to ask you to identify an infinite number of intervals. We might ask you to identify an infinite number of points of inflection.
And that's
Right.
like-
So if you wanted
that
to
weird notation.
points of inflection on that interval, pi over 2 plus, and what, it changes every pi units, right?
Yeah.
Every pi units, plus pi times k, where k is an integer. Right, so if k is 1, we have 3 pi over 2. If k is 2, it's 5 pi over 2. So k could be negative 2. Right, so this is how we would write this. You could write k is an integer, which is fine because you don't know German. That's okay. The German word for number starts with a Z. I think we taught you that last year when Leah was
It
here.
should be German. That's where you get the N. Z
Okay.
is a full letter.
It is. It's really.
Do you want me to show you one where the second derivative does not exist, or you think you can handle that? it's just, it would be something like, right, so the first derivative still exists, except at 0. No, that's still right. The second derivative is when we get the negative exponent. So the second derivative does not exist at 0. But you're still going to do a sign change analysis to check for a concavity change. This can still be a point of inflection. Okay. Check for concavity change. Good? Good enough? Yeah? I see some head nods. Okay, let's talk about the second derivative test. You know, I'd rather go sit in my chair and drink coffee, but this is more important. When I'm tempted to play video games, I say no and I do something more important.
Pretty impressive.
What?
Could you go back to the last page, please?
I'm sorry?
Could you go back to the last? Good. Okay, let's look at this function. Okay, for the second derivative test, what you're looking at is the critical points and the second derivative. So you need the first and second derivative still, right? So what's the first derivative? This is calculus AB's favorite problem right now. Product rule.
I like the power rule.
Yeah, I think that's probably their favorite right now, the power rule. It's so easy.
I think I like the chain rule of the product rule.
Okay.
The chain, like.
Okay, determine critical points. What did they come up with? Somebody came up with a kind of a fun jingle for the product rule. It's kind of gangster, actually.
Was it Cairo?
No,
It was Sean Doyle.
it was Cheyenne Etheridge.
Oh. Sean came up with one too, I think.
So what's the go?
That was the chain rule.
Oh, yeah, it was back.
Those side-eye. I'll think of it so you can put that in your toolbox. Okay, so if we're determining critical points,
You can only show us the
I'm going to factor this out because it makes it easier. And we get 2, negative 2 plus 2 is 0. Thank you. So this can never be 0, right?
Nope, nope.
And what would that give us? X squared equals 2.
Or, like, positive.
Thank you for correcting yourself. Okay.
That's weighted.
How do I determine, using the second derivative test, if that's a max or min? We're going to use concavity to determine min-max. Okay. Normally at this point you could use the first derivative test and do a sign analysis, right? That's what I would default to. But sometimes you're given a function that you can't, they'll like give you the second derivative and they'll give you the critical points. Okay. And you can't do a sign analysis, so your job is to plug those in to the second derivative, determine concavity. Okay.
So what's the second derivative? Why did I pick this function? Let's use that one.
Okay.
Sound good? That's the first derivative, right? Simplified. Second derivative. Okay. Now plug critical points in. Who made that funny sound? If I plug root 2 in, do I get a positive or negative? That's all I care about. Actually, that's definitely 0. It's a negative, because that makes it negative, right? And h double prime at negative root 2 is going to be a positive, because that makes it positive, right? Negative times a negative. All right, so at root 2 is a critical point, and it's concave down, maximum. Negative root 2, concave up, critical point, minimum, right? That's the second derivative test. Okay. Again, if you're given the function, just do the first derivative test with the sign analysis. But they will set you up to where you're given these, you don't even have to calculate them, and all you have is the second derivative of some nasty function. So you just plug them in and say min-max on concavity, okay? So that's kind of convenient that you're actually given the information you need. You just have to apply that test. Right. What happens if the second derivative is 0 at a critical point? Ideas? We don't know anything. Okay, this is the second derivative test is inconclusive. Okay. We have to use some other technique to determine min-max. Yeah. Use other method for min-max. All right? Keep that in mind. I think I'm done. Any questions? Good? Clear as mud? Well, go jump in the Colorado River. That's about what it is. Ooh.
Does that mean form B?
Yeah. Our first question from just the DC exam for the year. There you go. Let's check this tomorrow. Do you want a day, 2 days for this? Because I'm only spiraling for tomorrow night, so I'll give you 2 days. Is that cool? Okay.
When you say A, B, and NBC, does that mean?
It was on both tests as number 5. 3 of the problems are the same on both tests. which gives you guys a decided advantage, right? So you've already practiced 3 of those problems quite a bit. The other 3 are BC. One is going to be a series problem, guaranteed. One is going to be a parametric or vector, your particle motion problems. It's basically what it is, okay? And then the other one's probably going to be polar area, but those 2 kind of change. There's always a series problem, and the other 2 can vary a little bit here and there, but we'll get you there. Definitely. The series problem can be really difficult or really easy. It just depends on how they're feeling.